Okay, welcome everybody to UKCCSRC's Research Needs Workshop for Environmental Impacts. There's an etiquette which is there. Remain muted with your camera off during the presentations, and we're going to have 3 presentations and then a break, and then an opportunity for some question and answers afterwards. I think that's the format, isn't it, Caris? Yep, right. Then the next slide, please, Caris. So the agenda for today, introduction. Let me introduce myself, John Henderson, Environment Agency. I am the sector lead for combustion and also leading on carbon capture and a number of other net zero related to combustion type technologies. And then we have Simon from the HSE and Jenny from P66 to talk about the Humber cluster, and then David Graham from Uniper to talk about some monitoring needs, and then a break, and then we have a discussion session around prioritization and raising any other needs that haven't appeared thus far. Next slide, please, Caris. So the objectives, there's a number of workshops, clearly, and there was one yesterday on carbon capture. Today, this morning's one is environmental impacts, including health and safety. There's also one on storage, policy and public engagement, and transport, including monitoring by the looks of it. So you can get on an invite to those if you haven't already by registering, and these will all be put out on, or the results will be put out on UKCCRC's website afterwards. Next slide, please. This session now is really a repeat of one we did back nearly a year ago. And from that, there were a number of needs identified, which are still present and necessary for the environmental side of carbon capture and storage. So I'll just run through those quickly. And then we can include those in our discussions later. And any subtleties, needs, differences, etc. around those are welcome. So you can see them on your screen. First one, then, the modeling of emissions to air. The tool that contractors, operators, and ourselves use is known as ADMS, and there are a number of potential improvements to that modeling that we are all interested in, and they're broadly listed there. Then we have a request for looking at cross-media effects of acid washing on abating amines from post-combustion capture. Clearly, it's good at reducing emissions to the atmosphere, but then of course that leaves you with an acid solution with amines in, which has to be disposed of. So there's more environmental issues around that. Then we had one around identifying the ultimate fate of species emitted from carbon capture processes, and predominantly we're talking about amines and nitrosamines, or degradation products. Where do they go if they're emitted? Do they go to ground? Do they go to water? Do they survive a long time in the environment? All good questions we don't necessarily have answers to yet. Next slide, please, Caris. And so next we had what about larger effects of clusters, and if we had a large number of carbon capture plants, potentially all emitting amines or degradation products, we might saturate the environment, who knows. So there was a question around that, which is possibly a kind of planning one, I guess, but certainly one worth looking into in the future. Next one was about chemistry and chemistry of capture solvents and their breakdown, and environmental assessment levels. Those are the health-based levels that we in the agency use to assess potential impact on human health. So there were lots of questions around that. We have identified some, but there are plenty more to be developed, and we have a list, and others will also have interests in those. Then emissions from non-amine capture solvents. Again, we don't necessarily know what those solvents will be or what their emissions might be, but clearly quite important. Then another one on modeling. Monte Carlo modeling, a clever statistical method, and risk-based approach to modeling impacts. And last but not least, monitoring. There are lots of monitoring needs around carbon capture and storage. We're talking about new substances at very low levels, and there's stack monitoring for emissions purposes and ambient monitoring, clearly. We need new methods for both ambient and stack. And of course, we also need methods for monitoring CO2, but more of that anon. So that's my introductory slot, Caris. I think it's next is Simon from the Health and Safety Executive. Simon, are you okay to take over and do a 15-minute slot?
Oh, thanks for the opportunity to come and talk at this meeting. Okay, so to begin with, I wanted to take a step back to a paper that was published in 2007 by Steve Connolly and Lawrence Cusco from HSE. So at that time, quite a long time ago now, isn't it, 15 years? Yeah, there were a number of uncertainties to do with CCS because of its particular properties in terms of phase change. So this paper presented a number of those uncertainties and things that we ought to investigate for rollout of CCS. So things to do with dispersion modelling of dense phase CO2 and phase change behaviour, Joule-Thomson cooling and embrittlement steels, potential blocking of valves from solid CO2, particle scouring and erosion effects, so because CO2 is used for jet cleaning and cutting. Deposition of CO2 as a big dry ice bank, running ductile crack propagation along dense phase CO2 pipelines, equation of state and corrosion issues. So it was interesting yesterday sitting in on the capture meeting to hear about that several of these things are still issues even now, 15 years later. And some of that, the things in that paper were drawing upon incidents that had happened like this one, the Hungarian incident, a wellhead blowout that had led to a significant dry ice bank around the release point, and they needed to get in very serious sort of hot air blowers to gain access to it and melt the ice. So that things like this incident, this comes from an Energy Institute document. Maybe some other people on this meeting were involved in that. There's actually a new update to this Energy Institute document that's currently being drafted. I reviewed a copy of it a week ago. It's looking really good. So that's to do with hazard assessment of both onshore and offshore CCS. Marcella from the Energy Institute was in the meeting yesterday. I think I saw her on the list. So she's the main point of contact if you want to know more about that. And it's looking really good, the document. So people, if anyone here has contributed to that already, then they're good work. So yeah, in that period, sort of after 2007, about sort of a decade afterwards, there are a number of different projects that were investigating some of those knowledge gaps. So this is just a slide from showing some results of the work Shell funded at DNV Spade Adam, where they did some dense phase CO2 jet releases. And the aim of this was to understand, are these dispersion models any good at predicting the concentration and the temperatures downstream? We worked with Shell on that analysis and compared Shell's models and our models and things, and it showed that generally, yeah, the models actually can predict these things pretty well, which was a useful finding. And there were other projects that came along as well. So Caltrans was a really significant project led by National Grid. It involved, well, experiments were done at Spade Adam, some of them shown here. There were Atkins and pipeline integrity engineers, and a whole bunch of different universities were involved in that work as well. It was focused around sort of the scientific underpinning for that White Rose project. But yeah, did some really impressive work both on the experimental side and the model validation and everything. And HSE was involved in just sort of overseeing that project. So yeah, we're involved in those projects and a bunch of other things over this sort of 10-year period from 2007 to 2017. And there is an HSE research report available on the website if you're interested to know, have a quick overview of these different projects and what the main findings were. The scope of this meeting today then is really to try and look at knowledge gaps, I think. Since 2017, we've not been really focused on CCUS. After that, that last government competition was cancelled. We sort of withdrew from the scene. So I've got some ideas here of knowledge gaps, but some of them may have already been filled. And if they have, I'd be really interested in hearing from you about that. So yeah, on the capture plant, well, I should say as well, in that sort of 10-year period where we're more heavily engaged, we tended to focus mostly on the pipeline transmission aspects of it. So we're still getting up to speed on things like the capture plant. And I'm not sure, we need to have a look into it, but the risk from toxic amines and nitrosamines and so on. On the pipeline design, so looking at running ductile crack propagation, we're aware that that standard Patel 2 curve method is then applicable for dense phase pipelines. That was why in the White Rose project, I think National Grid went to full-scale testing to look at that material toughness requirement. So yeah, I'm aware there's this paper at the bottom of the screen there that's been published, but does that answer this question of is there a validated model for predicting these running ductile crack propagation? Yeah, interested to hear from people on that. In terms of corrosion regimes, it seems to be, I'm a fluids person, there's other colleagues who deal with the material side of HSE, but I'm aware that, making sure that the CO2 stream is dry and that you don't have any free water is pretty important. I don't know what happens if there's process upset conditions and the effect on corrosion rates, and learning lessons from projects around the world on that. In terms of pipeline risk assessment, in terms of failure rates, I think there's some work needed in that area, specifically on the fracture mechanics aspects in pipeline risk assessment models. That's a knowledge gap that we've got internally in HSE for our risk assessment models. There may be other groups on this call who are working on that. For other organisations, we'd be really interested to hear from you on that and how you're addressing those knowledge gaps. On the CO2 dispersion modelling side, so I said that it was kind of, we've got an understanding of that. But when it comes to the dense gas nature of large CO2 clouds, we've got two classes of models, I guess. The integral models like DNV Fast and TNO-FX and Shell-Fred and Drift. And they can run really nice and fast, but they assume that kind of the world's flat. And then we've got other models like CFD models that can handle the terrain, but take a lot of time to run and are computer intensive. But you can't really use those CFD models along the whole pipeline route if it's like 100 kilometers or something. So are there methods that can bridge that gap between those two classes of model that could be used as like a screening tool to tell you when terrain is important? I'm aware that there's people like Chris Dixon at Shell who have developed a shallow layer model for dense gas dispersion, which is like perhaps like a halfway house between the two. There seems to be a bit of a gap there that could be interesting to fill. and also looking at toxic risk methodology, incorporating sublimating solids. That's probably for dense phase pipelines where you're more likely to get large amounts of solid CO2, although you can get some solid CO2 with gas phase pipelines, I think. And as far as I'm aware, most of the UK projects are looking at gas phase onshore, dense phase offshore, but I might be wrong. So yeah, interested to hear from people on that. So that period when we were engaged on the CCS sort of projects, people weren't really talking about ship transport then, but obviously they are now with things like the Norwegian Northern Lights project. So I'm not sure we fully understand the impact of what would happen if you released a large amount of CO2 onto water. And I'm aware that there was a DNV project that did some tests at Spade Adam, and they were talking about doing some tests in the Scottish Lake. I'm not sure what happened to that, but that data is not freely available. So yeah, the issues there, things like rapid phase transitions that you see with other substances like LNG and liquid hydrogen. You know, what would happen if you released a large amount of cold liquid CO2 onto water? And the sort of scenarios there that we're looking at would be failure of loading arms or releases from ships. And I mean, a really useful thing that I haven't seen that would be, you know, really nice if some academic partners, maybe in collaboration with one of the major operators, could do would be to look at recent experience of both sort of CCS and the pipelines that you use for enhanced oil recovery in the US, and look at, you know, near misses or other incidents that have happened. There's a reference there to that Huffington Post article, which was a really interesting read about that incident in Mississippi on the CO2 pipeline there, where they had got valves that froze in the open position due to internal ice formation. So it's things like that that would be really useful to share. I think everyone's got an interest in making sure that CCS infrastructure is safe, that people aren't harmed. So hopefully, yeah, it'd be really good to review work in that area. And yeah, and finally, I guess there may be other knowledge gaps that we're not really aware of, but if you think, you know, we ought to know about them, please get in touch with us, because we've been a bit out of the loop in the last 5 years or so. Yeah, so I've probably underrun on time, but I wanted to leave a bit of scope for questions. So there's my email address there. My colleague Catherine Spriggs is also on the line as well. And yeah, that's it from me.
Thank you, Simon. That's excellent. Very interesting. Jenny, I think you're on next.
Great. First of all, thank you very much for having me. My name is Jenny Strutcliffe. I work for Phillips 66 at the Humber refinery, based on the south bank of the Humber near Immingham. I've worked there for 15 years, originally as a chemical engineer, then moving into environmental regulation, involved in managing the permitting for the refinery, and then also overseeing the process safety team and our COMA obligations. And just last year, joined the project team for Humber Zero, among other things, working on other decarbonisation projects as well. But involved in Humber Zero, particularly regarding the regulatory and health, safety and environmental issues involved in the project. And from having heard John speak already on previous areas identified, and Simon from the HSE, I would say that I'm not sure I'm going to add anything new in terms of particular research areas, but what I can give is a flavour of the project and what the activities that we've done so far, the particular HSC considerations so far. And yes, just give a bit of a kind of a practical flavour of how those things are influencing being used within the development of the Humber Zero project. So moving on, so the Humber Zero, I assume that most people on this call are probably going to be fairly familiar with the various projects and clusters and activities that are going on in the UK, but I'll give a quick overview of Humber Zero and where it fits within the bigger scheme of things, the right-hand graphic is a map of the UK showing relative emissions, carbon dioxide emissions from industrial emitters in the various locations in the UK. And that really highlights where our industrial clusters are, shows Humberside as the largest industrial cluster. And really these clusters are where the opportunities are for carbon capture and storage, because you have the high concentration of CO2 emissions, where carbon capture plants and carbon capture and storage can be the most effective at reducing significant quantities of CO2 going to atmosphere. Also the UK being very well strategically located near the North Sea and potential significant stores of carbon dioxide. The left-hand graphic shows Humber Zero. Humber Zero is a partnership between the Phillips 66 Humber Refinery and the VPI Immingham combined heat and power plant. They are very closely located near Immingham, along with a few other industrial emitters. And again, also located close to the development of 2 potential pipelines and storage solutions for carbon dioxide. So that's obviously great news, and ultimately we think all of these options are going to be needed to get to net zero and achieve the reductions that we need to achieve. And of course, one of those pipelines, the Zero Carbon Humber pipeline, the East Coast cluster, have been sequenced as a track 1 transportation and storage provider. So we are engaged with them and engaged in the phase 2 process. And so the carbon capture project, Humber Zero, involves carbon capture plants installed on the Phillips 66 Humber refinery to capture existing emissions from the refinery, and also on the VPI CHP. The funding was awarded for front-end engineering design that commenced in April last year and is likely to take us to March of next year, 2023. And that funding covers initial carbon capture of up to 3.8 million tonnes per annum by 2028. Both plants to come online earlier than that, so the full capture would be by 2028. And the wider Humber Zero project could involve the capture of up to 8 million tonnes per annum by that's meant to say 2030. That's a typo there. So 3.8 by 2028 and 8 by 2030. The initial capture involves retrofitting to capture the existing emissions. Longer term, there may be some blue hydrogen options to capture the full 8 million tonnes per annum, but the initial is purely a retrofit to capture existing flue gases. And the CO2 in the highly compressed form would be taken by pipeline for storage in the North Sea. And again, it's great project for safeguarding existing industry and protecting jobs in the region. A lot of people might ask why a refinery, why install capture on a refinery, but the Phillips 66 refinery provides a lot of essential products that are used by society today and will be used in a society going forwards, such as sustainable aviation fuel and graphite coke for electric vehicle batteries. So as mentioned, the funding was awarded last year. FEED started in April. Pre-FEED studies really started in April and concluded by the end of last year. And we're now in a FEED stage going through to Q1 2023. Environmental and planning assessments are underway. Our contractor was appointed in September, October time last year, and that's AECOM. So we have been working with them on getting that work started with a target of submitting planning and permitting applications in Q3 this year. All being well, we anticipate construction will be commencing in 2023, and Humber Zero will be coming online at the VPI combined heat and power plant in 2026. closely followed by the capture at the Humber refinery in 2027. So, as mentioned, what I can give is a bit of a flavour of what has been done on the project so far. The refinery is an existing upper tier COMA facility, and the VPI CHP is a lower tier facility. So we already are familiar with COMA and managing COMA risks. However, carbon dioxide not being currently classified as a dangerous substance under the COMA regs gives us a little bit of a regulatory gap. It's not covered by COMA. The relevant instrument would be the Health and Safety at Work Act, which would require us to manage all of our risks to a LARP anyway and protect people, but it wouldn't necessarily be covered by COMA. However, as already highlighted by Simon, a number of activities and reports have already been produced by the HSE of particular relevance for assessment in this project was the assessment of major accident hazard potential of carbon dioxide, and how carbon dioxide might be considered in the existing, with a bearing to the existing COMA regime and land use planning. So this was particularly useful. The report effectively concludes that carbon dioxide or high pressure releases of carbon dioxide does have major accident hazard potential, and therefore it should be assessed as such. So that's how we have approached managing the risks of carbon dioxide. We think that it does still leave a bit of a regulatory gap, because should carbon dioxide be covered under COMA, then there would be a formal process by which the HSE would be involved, and that would be through notifying them of potentially the additional dangerous substance that we would be handling on site, and depending on those quantities would then trigger its own COMA report, in essence. As it stands, the potential there is, the potential HSE involvement really is just in what update that might trigger to our existing COMA risks on site. So yes, we're seeing there's potentially a slight gap. As it happens, Humber Zero has been active in contacting the HSE with a close relationship through our existing COMA framework, and have a planned engagement session with them on the project so far, but still recognising more widely a gap in the framework. And really, from a project perspective, we think it is essential to understand that gap, to really close that gap, because the public is concerned about having that independent oversight of the projects, and that is really needed to maintain that public trust and public confidence in carbon capture and storage. And aside to that, of course, early involvement is better to avoid any potential delays with involvement at a later stage, and then having to maybe build in considerations raised at later stages. So really essential for early involvement and early oversight from the HSE. So one of the key issues that we identified early on is the location of the CO2 high pressure booster compression. So this is getting the carbon dioxide from 20 bar G up to 135 bar G for entry into the transportation and storage network. And this really presents the main COMA risk from the carbon capture plant itself. And so one of the early considerations is where to site the high pressure booster compression location, and would there be any limitations over the siting of the booster compression for the project. And so initially we carried out a siting study. This map that you can see in the graphic shows the Phillips 66 Humber refinery to the south. You can see there's a railway line that's segregating the refinery from the adjacent Lindsey oil refinery and the VPI combined heat and power plant, which is sort of in the middle to the east there. We identified potential sites, and I should say that these sites were identified due to kind of technical considerations and not considering any commercial considerations at that stage. They're not necessarily within the ownership of the partners, but this was a technical feasibility study. So site 2 and site 5 show where the carbon capture plants themselves would be located. So then it was a case of can those can the booster compression be located close to those carbon capture plants, or in land, nearby, adjacent to them. And so the study was carried out very much in line with the guidance that the HSE has issued using fast modelling. It covered the entire quantity of CO2 and not kind of split, since the carbon capture plants themselves will be split for the Humber refinery and the BPI. The booster compressions may also be, but this looked at the entire quantity and was a relatively sort of conservative screening study, as you might expect. So the output from this study, what we were looking for basically, is there any of the sites that would be ruled out, or any of our options ruled out on the basis of doing a study to review the location-specific individual risk and land use planning methodology. And these contours show for one of the sites. This is one of the sites for the carbon capture plant, as to what the contours would be and how that covers the site, basically. Again, should say this is an early layout of one of the carbon capture plants, so it's not necessarily still that way. But in principle, the location-specific individual risk was assessed for a person outdoors, a person indoors, and then land use planning contours were also reviewed. And as you can see, the red, the sort of intolerable line, is kind of within the site, doesn't travel off site. Any of the contours that go off site are all in the tolerable, if a LARP region for the site. And the same from a land use planning perspective. Reviewing the guidance, there's multiple kind of layers and considerations to the guidance. When you're looking at the inner, middle, and outer zones, and what the sensitivity levels are of the boundaries to the site, the areas immediately adjacent to the site, or the areas affected by the contours. And these contours appeared similar as you applied them to all of the options that we reviewed, all of the locations 1 to 6. And so the conclusion from that study was that none of the sites that we were considering would be excluded on the basis of the QRA and location-specific individual risk or land use planning, and so that we could progress with on a technical basis and a commercial basis with the booster compression location that best fit the projects. And mitigations for these would be developed through engineering design. And as we've then moved on from that, then really the questions have been about the integration of the capture plants into the existing site. So for the Humber refinery, that's the interbase with an existing COMA unit. The emissions are being captured from a COMA installation. So the capture plant sort of integration into that, and then the considerations of booster compression and the risks from that. And of course, mitigations will be developed through the detailed engineering design to return that risk to as low as reasonably practicable. Potential areas for further work, of course, these are the studies that have been done on the face of it. The report that I've referenced highlighted that more work was needed on assessing the dangerous toxic load, release frequency, and modelling of carbon dioxide releases. We think that there needs to be some more work on how this risk is going to be regulated. I haven't written on there, but the sharing of best practices and the development of best practice mitigations for carbon capture plants and CO2 booster compression. Again, there's been some work done on the public perceptions of major accident hazard risks of carbon dioxide, but we think again there's potentially more that could be done to understand how the public might respond to particularly the major accident hazard risk of carbon dioxide. So moving on, so that was really kind of a HSC coma concern. Environmental issues, again, I don't think I can add much to what has already been previously well documented and highlighted by John at the beginning. Emissions of amines and amine degradation products to atmosphere, further work needs to be done, particularly on the potential impacts of the various solvents and monitoring of ambient air quality for amines. So that's an area that needs further work. But the development of BAT for post-combustion capture, again, well documented through the collaboration led by the UKCCSRC. But particularly utility demand, minimising water consumption, because from a regulatory perspective, we're getting a strong steer from the Environment Agency that increased water demand is not going to be acceptable, and we're going to need to manage within our existing water usage. So development of the plants and best practices to meet that requirement is going to be something that we need to address. And from a practical perspective, again, this has already been mentioned, but this gives a bit of a flavour of our current setup and what we are looking at potentially moving towards. This shows a very simple schematic of the FCC as it is set up. The current capture plant is for capture of the FCC emissions, the fluid catalytic cracker that is. And so this is regulated under environmental permitting. It is also covered by the emissions trading scheme, for which, anybody that's familiar with that knows that there is fairly extensive auditing and checks and reporting that go into this. The FCC has to meet an uncertainty of 5%. And the current metering setup involves a flow meter on the air inlet to the regen section of the FCC and an inerts balance around the nitrogen on that basis. The SEM on the flue gas from the FCC tells you your components, what the nitrogen is in the emissions, what the nitrogen is based on the flow meter, the airflow meter going into the FCC, and therefore you can accurately quantify your emissions on that basis through partial measurement and calculation. And that is required to meet the uncertainty of 5%. It typically meets an uncertainty of nearer 3%. For the carbon capture plant, of course, this is going to need to be adapted. We are, of course, looking at fiscal flow meter on the outlet of the carbon capture plant. However, this is likely to be flow meter and composition, of course, to meet the certainty. And I would add that really, where we are seeing limited understanding is that any quantification of carbon dioxide is really going to involve a flow meter and the composition, and there will be an element of calculation involved in that to get the CO2 flow. I'm not sure that this is well understood at a policy level, so it could be that some further studies, further work on how this is actually going to work in practice would be useful. We're not sure how the existing SEM will be affected at this stage. We haven't reached that level of design yet as to whether that SEM will still be on kind of an active part of the ducting that currently goes from the FCC to the stack. So it may be that is not useful during the operation of the carbon capture plant, and therefore meter composition will be needed. As it stands, the bays have indicated that they would like that to be a fiscal flow meter as well. That may change, that may develop, but I'm not sure. That again presents a potential challenge. The fiscal flow meter on the outlet of the carbon capture plant, that you get higher accuracies for smaller diameters of pipe, so you probably would lose some of the accuracy of a flow meter for the inlet of the carbon capture plant, which would have a greater diameter of pipe. So there's really some key practicalities around the metering of the carbon dioxide going into the plant and going out of the plant that need to be resolved. And again, there have been a number of reports that have identified these issues and highlighted these potential gaps. Using those as a reference, but these really have identified issues that we now as a project are trying to work through the practicalities of. And the carbon capture plant will have a new vent to atmosphere. And again, that new emissions point will need monitoring, SEMS monitoring for the components. Amines have, of course, been mentioned already as one of the key aspects, but it will also need to cover potentially the other parameters that we currently monitor for the FCC, even though they may have been greatly reduced through the new design. But in any case, we're looking at needing SEM and flow meter for the emissions from the carbon capture plant. And again, that will need to achieve a level of accuracy, and there's a number of challenges there. The flue gases without reheating would be at between 40 and 50 degrees C. Monitoring of cold flue gases again presents it's not possible for various parameters, and I understand there needs to be a balance between heating, having hot flue gases, heating the flue gases, but then you're potentially getting degradation of amine products. So a number of things that need to be resolved there, and this really gives a bit of just a flavour of how some of these research needs are needing to be considered in the development of a project like Humber Zero. And that was it from me. Happy to answer any questions or.
Brilliant, Jenny. That's excellent. Thank you very much for that. And we'll do questions and answers after we've had a break. But I think that's excellent running on into monitoring. And hopefully David Graham is there and ready to present his bit on monitoring. So off you go. Thank you very much.
Well, you see that we're in the programme talking on behalf of UNIPA, but actually we'd like to give a broader power industry perspective on behalf of JEP, which is the Joint Environmental Programme of the electricity supply industry. Steve Griffiths has supplied some slides on air quality impacts that I've incorporated here. For those of you who don't know JEP, we're not a trade association, that's Energy UK. We're more of a technology grouping, and the objective of JEP is to better understand environmental science and environmental impacts associated with the production of electricity from the full range of fuels. We do have a small work programme which we develop each year, and that's really aimed at informing the industry's response to developing legislation, offering technical material in support of permitting activities, and that includes specific discussions with the UK regulators, who we meet with on a a regular basis concerning power station operations, and offer support materials to member companies on policy and legislative developments. You can see the list of current JEP companies at the bottom. There's 8 major generators there at the moment. So I've started with a bullet point summary of headline research needs, and then I'll say a bit more about the first 3 of those. So these have already been mentioned, of course: measurement of amines in flue gas, air quality assessment. This is looking at amine chemistry post-emission. I've got measurement of emitted CO2, so this is uncaptured CO2, as a separate topic, which Jenny has touched on. And although this is beyond our ambit, and I don't have any slides on it, it's also beyond my personal expertise. CO2 security is obviously of paramount importance from an environmental point of view, and that might be being considered separately later in the week. But, you know, just thinking about it myself, is there a role for underwater acoustics in listening for leakage? Reservoir modelling must come into it, geological sequestration, and all the stuff relating to wellhead capping. So they're just a few thoughts on that topic, which I hope will be picked up elsewhere. In terms of measurement of amines in flue gas, well, the primary, secondary and tertiary amines are determined by the number of alkyl groups that are substituted into the ammonia molecule. So one alkyl group substituting one hydrogen atom is a primary amine, and so on. Most of the material in this slide is taken from a presentation by Mark Elliott given at the Air Quality and Emissions Conference in October last year. So one concern is direct emission of absorption solutions, monoethanolamine and a host of others potentially. And then amine reaction products, nitrosamines and nitramines. The implication being that NO and NO2 involved in their formation. In terms of measurement, the agency's technical guidance note lists these sorts of approaches. So it's technical specification 13649 for sampling, which is based on sorption tubes. Occupational health standards for the analysis. So NIOSH 2002, which looks at aromatic amines. 5 substances are listed there. And NIOSH 2010 looking at aliphatic amines. Only 2 substances listed there. So therefore there's a question about applicability as you look at the wider range of potential components. And the method there is gas chromatography with a flame ionization detector. Limit of detection is about 0.1 milligram per sample. I don't know what that is offhand in terms of a flue gas concentration. I'm guessing it's small, given these are occupational health standards. And then TS 17337 Fourier transform infrared analysis. So this is a continuously measuring instrument, looking at a raft of different species across a wide spectral window. Of course, you need some idea of what's present in order to get the analysis right. Limit of detection is about 1 part per million, so reasonably high, you might say. So in terms of research needs, well, further method development and validation, definitely. The methods need to be checked for the full range of species that might be encountered, or at least a range of representative species. This limits of detection need to be low. New techniques may be required. And of course, ambient monitoring needs to be thought about as well. So that's just one slide on amines in flue gas. In terms of air quality assessment, well, we already, the gas-fired plant, we would already assess for the NOx components, CO. we'd probably screen out PM2.5. Exceptionally, we'd consider formaldehyde. But of course, in addition to those species, there's a number of others post-capture that we need to consider. Amines, nitramines, nitrosamines, associated with solvent carryover and degradation. And that can occur both within the capture plant and following emission to air. And whilst these species are only emitted in trace amounts, some species, notably key nitrosamines such as NDMA, have high toxicity or may be carcinogenic, so they need to be rigorously assessed. And it's important that those air quality assessments are robust and include worst case assumptions to provide assurance to both regulators and other stakeholders that there are no significant negative impacts on health or local ecology. Right, so that's those points. And then in terms of emissions, emission levels are most reliably established through pilot plant projects, but can also be supported by the modelling of plant chemistry or estimated by the vendor based on similar industrial applications. In terms of the conversion process in the middle there, amines can react with OH radicals and NOx species in the atmosphere to form nitrosamines and nitramines, and they in turn undergo a range of reactions, including for nitrosamines photolysis, so they're destroyed by UV. And the reaction rates and the stability of the degradation species are highly dependent on the amine or amines present in the solvent. There's also very little measured data on background concentrations, although they're likely to be very low, as few processes generate those emissions currently. And there may also be competing reactions or actions between different species where a solvent contains several amine components. Those issues associated with emissions to air are also applicable to emissions to water and to transformation of these species in water or soil following deposition from the air. And finally, on the right-hand side, we need reliable air quality standards or environmental assessment levels to assess the results of dispersion modelling against. And of course, the Environment Agency is currently looking at that, but currently there are only formal assessment levels for MEA and the nitrosamine NDMA. Of course, you could look at occupation exposure limits, effectively multiply these up, which is a very conservative approach, and toxicity studies are also required where they exist, and vendors would be expected to provide some supporting data in relation to the ecotoxicity and exposure limits for their standards. So chemical safety data sheets there. The right-hand image there is just a screenshot of input into the dispersion modeling model ADMS, and then the amine chemistry module is illustrated on the bottom left. That's the only model endorsed by the agency at present time. And of course, it's a simplified reaction scheme to cover key reactions controlling atmospheric concentrations. So the basic chemical scheme covers key species of interest that we've already mentioned, and their reactions with OH, NO and NO2, as well as the photolysis of nitrosamine. Currently, there are very few amines for which the full set of chemical reaction rates and branching ratios are available. Schemes based on MEA and DMA have been presented in air quality assessments for capture plants. However, solvents in the market include a range of different amines, and you may have multiple amines within a single solvent. So it's important that reliable kinetic data is available or can be derived on a sensible time scale it's also important that reaction rates are representative of the chemical steps in the model input, which may in reality be a combination of several reaction steps due to the simplification scheme. So just wrapping up on air quality assessment then. We've mentioned that schemes are well established for a couple of amines. Reaction rates can be measured experimentally, for instance using bag experiments, where the relevant mix is introduced into a sealed area and the formation rates are monitored. Alternatively, individual steps can be measured by reacting the species in reaction cells. And those approaches can be time consuming, but will help to build up information for new species. And then once a suitable database is established, it may be practical to estimate reaction rates based on factors such as similarity of structure, molecular structure. So you'd expect similarities in reaction schemes for primary amines compared to secondary amines, and in turn compared to tertiary amines. And as we've already mentioned, similar understanding of species conversions is required in soil and water. And for environmental assessment levels, a wider understanding of the potential toxicity of different amines is required. So literature reviews, toxicological studies to build up of understanding, and again estimation of toxicity based on structural similarity, functional groups, etc. would be beneficial. And are there other ways of doing that? The capture projects are already going through planning applications and permit applications, so there's an urgent need to progress research in these areas, ideally over the next 12 months. Establishing a program which prioritises the most important amines and degradation species is important, taking into account those amines most likely to be used and those which can provide the broader database of useful information. And of course, the scope for input from vendors, operators, regulators, and research teams. So I suppose saying there, that's really a plea for a joined up approach and people talking to each other, maybe having a group which meets to consider that. And it's probably worth emphasizing that the releases are really in trace concentrations, and the lack of knowledge is driving us towards having extensive sensitivity studies and using worst case assumptions, and that in itself is an issue. So that this information is urgently required. So the third topic then, measurement of the emitted CO2 mass release. Currently, it's assumed that emitted CO2 is determined by difference. So this is the carbon into the process, which at the moment is determined from the emissions trading system. And we would argue that should continue to be the case. We have a much more accurate input based on the metered fuel in, the fuel composition, than we could get from using flow SEMS upstream of the capture plant. That is the reality. So it's the CO2 entering the process from the fuel consumption and fuel quality, and then the metered CO2 to storage, and the difference is the emitted CO2. For combined cycle gas turbine plant, that emission is a small difference between two large numbers. So 1 normal meter cube of natural gas going into the process gives just over 1 normal meter cube of CO2 entering the capture plant. And if we capture 93.5% of it in this particular example, we get 1 normal meter cube of CO2 being metered to storage. So the volumes of fuel metering in and the volume of CO2 to storage out are very similar, and the difference that we're emitting to the atmosphere in volume terms is small. Assuming that the metering conditions and the meters are similar for natural gas and CO2, it's likely to be slightly higher uncertainty for CO2, I would think. But let's say the uncertainty contributions are comparable and they're combined in this way, in square root approach. So for 1% metering uncertainty, we get a 1.4% overall uncertainty based on the metered quantities, so based on the larger numbers that we're metering. If we think about that same absolute uncertainty in relation to the amount that's emitted post-capture to the environment, of course, in relative terms, that's now very high. And this is just formally illustrating the difficulty of determining something as a difference, small difference between two big numbers. If we look at the sensitivity to capture efficiency, so metering uncertainty is typically in the range 0.25% to 1.5%. So 1% would be a guarantee value, 1.5% is the maximum that's allowed, and maybe 0.25% to 0.5% is the best that can be achieved in practice. We've considered the uncertainty in the carbon content of the fuel going in and the purity of the CO2 coming out, and assigned a low uncertainty to that we've taken into account. And we've assumed that the metering is essentially identical, but have taken into account changes in volume between natural gas and exported CO2. And you can see here the uncertainty in the CO2 emission, mass emission to the environment, versus the metering uncertainty along the x-axis. So at the 1% metering uncertainty that is guaranteed, even at a low capture rate of 90%, we're approaching 15% uncertainty on the final emission. For a high capture efficiency, that's approaching 60%. Now that of course can be improved by improving the metering uncertainty, but you still can't get away from the issue of a relatively high uncertainty on that small number. So that would push us towards direct measurement of CO2 and stack flow rate in the final emission. In terms of CO2 concentration, that's already quite low for a gas turbine. It's about 3.5% by volume at reference conditions. And for a range of turbine designs and a range of operation, you're anywhere from 5% by volume, dropping off as you go down in load. Post-capture, of course, the CO2 concentrations are very much lower, so less than 0.5% by volume typically at the same conditions. And you can see that obviously as the capture efficiency increases, these concentrations drop even further, so you're down to sort of 0.1% by volume level. And some account needs to be taken of the ambient air concentration, of course, at these levels, and decisions made about CO2 entering the process in the air should be considered to be inherent and not counted in any of this. So that's concentration for the final emission. Stack flow rate, well, direct measurement is difficult in large ducts. It's much harder than when you're measuring in a small pipe using physical metering. You require cross-duct flow meters, and they need calibrating. So ultimately, you're constrained by the uncertainty of the test method that you're using to calibrate the meter. So it is probably better to rely on calculation. We know what the stack flow is from the fuel consumption entering the process, and then we can then correct it for the removed CO2 which we will also have measured. So in summary on this particular topic, the uncertainty of calculation of emitted CO2 is likely to be too high for capture efficiencies greater than 90%, which pushes us to direct measurement. That's challenging due to low CO2 concentrations and the low uncertainty target. So it requires good CO2 measurement and test methods at low concentration, further standards and guidance in that area, further consideration of background CO2 in combustion air. It also requires good stack flow calculation with a low uncertainty, which we believe is doable. UNIP has also developed a tracer technique for calibrating stack flow meters and for verifying stack flow calculations. That's based on helium injection. So we can talk maybe in the discussion about research that would need to be undertaken to make sure that those calibration approaches are valid. Now, I'll just point out this is just a first look see that we've already discussed with the regulators. It contains a number of approximations and assumptions that we will need to refine. We'll be looking at this ourselves, but there is scope for research in this area. I think that's all I want to say, John.
That's brilliant, David. Thank you very much. No, I think that's great. So there's a number of things we can talk about. We're up for a short comfort break now. Karis, I think that's normally 10 minutes. So if we make it back just before 20 past. Karis, I think before people disappear, we're going to have something called the Jamboard, where you can add your thoughts on Post-its. If anybody gets back early, they could start adding their thoughts to those.
Yeah, we'll pop the link in the chat so it's there ready for people to start adding.
Okay. All right. So see you back at 20 past.